In this video, we will work some examples of computing volume using integrals. Recall that if the cross-sectional area of some figure is given by a of x, then the volume of the solid is the integral of a of x over the values of x in which the solid presides. Let's work an example. Find the volume of a pyramid with a square base. Let h be its height and L be the length of one of the sides of the base of the pyramid. To do so, let's picture this pyramid with its tip at the origin and the center of its base at the point h, 0, 0. Now, if we cut the pyramid at some x value, the cross-section will be a square. Let c be the length of one of its sides. Then a of x, the cross-sectional area, is given by c squared. So now we need to find c. Looking at the pyramid from above, that is, the direction of the z-axis, we see the following picture. If we cut these triangles in half, we have similar right triangles. Therefore, c over 2 divided by x is equal to L over 2 divided by h. Solving this equation for c gives c is equal to Lx over h. Therefore, the cross-sectional area a of x is equal to c squared, which is Lx over h squared. Notice that our pyramid lies in the range of x's from 0 to h. Therefore, our volume is the integral from 0 to h of a of x, which gives us that the volume is the integral from 0 to h of L squared x squared over h squared. Computing this integral yields that the volume is L squared h over 3. Let's move on to another example. Compute the volume of a sphere of radius r. A sphere is a type of object called a solid of revolution. To obtain a solid of revolution, take a region and rotate it about some line of symmetry. The sphere is obtained by rotating about the x-axis the half circle that is bounded by the curve y equals the square root of r squared minus x squared and the x-axis. Notice that when you do this, the cross-section is a circle of radius square root of r squared minus x squared. Therefore, a of x is equal to pi times this radius squared. Namely, a of x is equal to pi times the quantity r squared minus x squared. To obtain the volume, we integrate a of x from minus r to r, which are the values of x in which the sphere lives. This integral is fairly straightforward, and if you go through the motions, you end up with the answer 4 pi r cubed over 3, which is the number we were supposed to get through our knowledge of basic geometry. Let's work another problem with solids of revolution, this time with a little bit of a twist. Let R be the region bounded by the parabola y equals x squared and the line y equals 4. Find the volume of the solid obtained by rotating R about the line y equals 5. Here, when we take the cross-section, it's no longer a circle. There's some space missing in the middle. We refer to this shape as a washer. And if you haven't seen a washer before, here's one for you now. So what is the area of a washer? Well, a washer is a big circle with a little circle missing in the middle. So, we could take the area of the big circle and subtract off the area of the little circle. So, the area of the washer will be pi times the outer radius squared minus pi times the inner radius squared. In this problem, our washer has inner radius 1 and outer radius 5 minus x squared. So, the cross-sectional area, a of x, will be equal to pi times 5 minus x squared squared minus pi times 1 squared. Boiling this all down, we get pi times x to the 4th minus 10x squared plus 24. Notice that the x values in which our region lives is negative 2 to 2. And so, our volume will be the integral from minus 2 to 2 of pi times x to the 4th minus 10x squared plus 24. Computing this integral, you get 832 pi over 15.